Hello dear students, in the last class we studied about Young's double slit experiment. In today's class we will obtain an expression for the optical path difference. The optical path difference of the rays coming from the two sources in an Young's double slit experiment, and we will also formulate equations for conditions for brightness and darkness, that is conditions for maxima and minima in the case of an Young's double slit experiment. From that we will try to find the equation for fringe width. So first of all, let us try to derive an equation for the optical path difference in the case of Young's double slit experiment. So as we have already learned, there are two different concepts. One is path difference, the geometrical path difference, and optical path difference. So if we look at this picture, this is the Young's double slit experiment. Here we have two sources. The first source is S1, that is the slit number 1, from where we have an electromagnetic radiation coming out, the light waves coming out. Similarly, we have slit number 2. From there too we have the rays coming out. It is spreading out into the space like this. So these waves are coming and interfering with each other, resulting in constructive and destructive interference at different points. Now if we want to find the different conditions that we get on this screen that is placed here, this is the screen. This screen is at a distance d from the sources. Depending on different positions on the screen, its distance towards the sources, we will have brightness or darkness at different points. In certain points we will have constructive interference, meaning we will have brightness. In certain other points we will have destructive interference, meaning there will be darkness. So just go to the last class and refer to the conditions of maxima and minima to understand how that happens. So as we have learned, constructive interference will happen when the light rays coming from the two sources interfere constructively at a point, and destructive interference happen when two waves meet destructively at a point. So here as you can see, from source 1, slit 1, light wave is coming up to here. From source number 2, light wave is coming up to that point, and if they meet constructively at that point, we will have brightness. So brightness goes hand in hand with constructive interference. So that is what we already know. So before moving on and finding out the equations for maxima and minima, we need to determine the equation for optical path difference between the light waves coming from source 1 and source 2, because then we can find the equation delta is equal to m lambda for constructive interference or brightness, and we have delta is equal to 2m plus 1 into lambda by 2 for destructive interference or darkness. So to state both these equations, we need to find delta, which is the optical path difference. So let us formulate an equation for that. If you look at this picture, you can clearly see light waves coming from source 1 and source 2 has to travel different distance to reach a point P. Consider an arbitrary point on the screen P, which is at a distance x from the center point, middle point. So we have slits S1 and S2, its middle point is M, and the point that is exactly straight to this middle point is the center O. From the center O, we consider a point at a distance x. We assume that the two slits S1 and S2 are at a distance d from each other. So from the middle point, the slit S1 will be at d by 2 length, and from the middle point, the slit S2 will be at d by 2 length. When the light waves start from S1 and reach P, and similarly a light wave start from S2 and reach P, clearly they travel different distance. S1P is lesser than S2P, right? From this slit 2, light wave has to travel an even greater length to reach P. So what is that path difference? First of all, let us find the geometrical path difference. The geometrical path difference multiplied by the refractive index of the medium will give the optical path difference, delta. Since in this case light wave is propagating through air whose refractive index is 1, geometrical path difference and optical path difference are equal. So we just have to find the geometrical path difference between these two. So how can we find that? Normally, in order to find the optical path difference, we draw a perpendicular from one of the points, source, to the other one. So S1n is a perpendicular that I draw from the first source to the second ray. From this point n onwards, the length S1P and NP are equal. So I can say S1P is equal to NP because we draw a perpendicular like that, right? From the point n onwards, if you measure up to P, that length will be equal to the length from S1 up to P. So for a ray starting from the source S2, the length travelled by it from n up to P is the same as the length travelled by a light wave starting from S1. So what is the extra distance that is travelled by the second ray coming from S2? This distance S2n is the additional length that is travelled by the second ray. After that, both of them go the same distance. S2P and NP are equal. Sorry, S1P and NP are equal. S2P is NP plus S2n. This S2n is the additional path travelled by the second ray. So we can say that if S2n, which is the geometrical and optical path difference, if that is equal to m lambda, then we have constructive interference. Similarly, if this S2n is equal to 2m plus 1 by lambda by 2, then it will be a destructive interference. So that will actually depend on the position of the point P. So let us formulate an equation for this path difference, which is S2P minus S1P. That is the path difference, right? That is the extra distance travelled by the second ray. So we have delta is equal to S2P minus S1P, the path difference between the two rays. Now, in order to write the equations for S2P, we consider the right angle triangle S2PF. So in this triangle S2PF, so this is the triangle from S2 up to P, from there up to F, and from F up to S2, we have a right triangle. And for the hypotenuse S2P, I can write an equation S2P square is equal to the distance PF square plus S2F square, right? PF square plus S2F square. Now clearly this S2F is equal to the distance between the screen and the slit, which is capital D. So instead of S2F, I can write D square. And for PF, we know PF will be the length X, which is the distance from O up to P plus D by 2, right? So X plus D by 2 is PF. So I can write this S2P is equal to S2p the whole square is equal to pf square, which is x plus d by 2 the whole square plus S2f, which is d square. D square plus x plus d by 2 the whole square will give you S2p square. Similarly, to write an equation for S1p, we consider the right triangle S1p E as our right triangle. So this is the right triangle we have. This is 90 degree here. Now what will be S1p square? It is the hypotenuse. So S1p square is equal to PE square plus S1E square. Clearly S1E is distance D. Now what is PE? PE is this distance. PE is equal to x minus d by 2, right? From O up to P we have distance x, and from O up to E we have distance d by 2. So PE will be x minus d by 2. So this is equal to x minus d by 2 the whole square plus d square. So we have two equations in our hand. One is that S1p square is equal to x minus d by 2 the whole square plus d square, and S2p square is equal to x plus d by 2 the whole square plus d square. Now let us find the difference S2p square minus S1p square. So we have to put brackets here. It is S1p square. Now let us find S2p square minus S1p square, which will be x plus d by 2 the whole square plus d square minus x minus d by 2 the whole square plus d square. Now expand each of the terms here. Here we have x square plus 2 times x into d by 2, which will be x into d, plus d by 2 the whole square, which will be d square by 4 plus d square. So a plus b the whole square expansion plus the other term, which is d square, minus x square minus xd. 2 into x into d by 2 is xd plus d square by 4 plus d square. So these are the terms in the second bracket. So when we take the difference, many of the terms will cancel out like this. So x square and x square will cancel out. D square by 4 and d square by 4 will cancel out. Capital D square and capital D square will cancel out. And the only term that remains are x by d and minus x by d. So xd minus xd, which is 2xd. So I can write S2p whole square minus S1p square is equal to 2xd. Now this is of the form a square minus b square, right? We have a square minus b square is equal to a plus b into a minus b. So this will be S2p plus S1p multiplied by S2p minus S1p. So this is S2p is our a and S1p is our b. This is of the form a square minus b square. So we have a plus b into a minus b. So that is equal to 2xd. Now let us write the equation for S2p minus S1p. That will be equal to 2xd divided by S2p plus S1p. Now we are going to make an assumption, a wide approximation. We approximate that for the denominator S1p is equal to S2p, which is approximately equal to d. So for the denominator part alone, I approximate that S1p is equal to S2p is approximately equal to the distance between screen and the slit D. So for here this part you can write D plus D. This is equal to 2xd divided by D plus D, which is 2D. So what will be S2p minus S1p? S2p minus S1p is simply 2xd divided by 2d, which is xd by d. So that is the path difference between two rays coming from slit 1 and 2, which is reaching at the point P. Here x is the distance of the point P from the center O, and small d, d is the distance between the slit 1 and 2, that is small d. Capital D is the distance between the slit and the screen. Now given this path length, path difference delta, this is equal to delta, let us write the equation for bright fringes. We know that bright fringes happen when the path difference is an integral multiple of lambda. When the waves meet constructively, we get bright fringes. So what we have to write is the condition for constructive interference, which is given by delta is equal to m lambda. Here delta is equal to xd by d. So I can write for a bright fringe to be obtained at the point P, the condition will be xd by d, which is delta, is equal to m lambda. If this condition is satisfied, you will have a bright fringe. Here m stands for different integers. M is equal to 0, 1, 2, 3, etc. The position that you obtain for x by substituting m is equal to 0 is the 0th order fringe. So when m is equal to 0, we have xd by d is equal to 0, which implies x equal to 0. That means at the position x equal to 0, you will have a bright fringe. What is the position x is equal to 0? X is equal to 0 is the midpoint of this screen, right? This is the x equal to 0 position. So at the midpoint, you will have a bright fringe in the case of Young's double slit experiment. After that, the next bright fringe will be obtained at the position you get by substituting m is equal to 1. That corresponds to xd by d is equal to lambda. At that point, you will have the next bright point, xd by d is equal to lambda, means x is equal to lambda d by d. At this point, you will have the next bright band, which is the first order bright fringe of the Young's interference. Then the point that you get by substituting m is equal to 2 is the second order bright fringe. So here you have the screen. The first order bright fringe is at the center. After that, at the neighboring point, you will have the 0th order bright fringe is at the center. Then you have the first order bright fringe. Then you have the second order bright fringe, and so on. So you will have the same to the bottom side, first order, second order, and so on. So this is how the bright fringes are distributed in the Young's double slit experiment. In between these, you will have dark fringes, as we will see now. So let us look at the positions of dark fringe in the case of Young's double slit experiment. We know dark fringe happens when we have destructive interference. What is the condition for destructive interference? Destructive interference happens when the path difference delta is equal to 2m plus 1 into lambda by 2. What is delta here? We have derived the expression for delta to be equal to xd by d. If that is equal to 2m plus 1 into lambda by 2, then we have destructive interference or dark fringe in a Young's double slit experiment. So substituting when m is equal to 0, we have x d by d is equal to 0 plus 1 into lambda by 2, which is lambda by 2, which implies x is equal to d lambda divided by 2d. So this is the position of the 1st order dark band. Putting m is equal to 0 will actually give you the 1st order dark band. Here m varies from 0, 1, 2, etc. So what will be the position of this point d lambda by d? It is actually exactly in between this x equal to 0 and lambda d by d. That means the dark bands are exactly at the middle point of these bright bands. So this is the 1st order dark band. This will be the 2nd order dark band, and so on. Similarly, to the bottom side you have dark bands. So these are the bright points here, separated by dark bands. This is the 1st order dark band and its position is d lambda divided by 2d. Similarly, substituting m equal to 1 will give you the 2nd order dark band. So let us derive that. When m equal to 1 in this equation, x d by d is equal to 2 into 1 plus 1 divided by lambda by 2. That is x d by d is equal to 3 lambda by 2, which implies x is equal to 3d lambda divided by 2d. So that is at a point 3 by 2 d lambda by d. So if you find that, this is that point. In between 1st order and 2nd order bright band, you will have the 2nd order dark band. So similarly, we will have certain points of bright bands separated by dark fringes in Young's double slit experiment. So this is like this. We have the initial source, which is splitted into 2 by S1 and S2, 2 sources, and from these 2 sources we have waves coming in. They interfere and will give you the Young's pattern, the interference pattern on the screen. You have the central bright band, then the 1st order bright band, and so on. In between that you have dark fringes, the dark bands. So at these points we have the constructive interference happening, and at the dark points we have the destructive interference happening. Now let us also find an equation for the fringe width. Fringe width beta is defined as the separation between 2 bright bands or the dark bands. So let us write the equation for the bright band. The bright mth order bright band happens at the position xm equal to m lambda d by d. Right? We had written that equation here. For a bright band, x d by d is equal to m lambda, or x is equal to m lambda d by d. That is the position of mth order bright band. Then what will be the position of m plus 1th order bright band? It will happen at the position xm plus 1 is equal to m plus 1 into lambda d by d. So what is the difference between these two? We have beta, which is the separation between the neighboring bright bands. That means xm plus 1 minus xm, which is equal to m plus 1 into d lambda by d minus m into d lambda by d, which is equal to d lambda by d. So this will be m d lambda by d plus d lambda by d minus m d lambda by d. The terms will cancel out and the remaining term will be d lambda by d. This is the equation for fringe width beta. Even if you do the same procedure with the equations of dark bands, you will get the same equation. That means the bright bands and dark bands are equally separated in the Young's interference pattern. And the beta is equal to d lambda by d. This means that the bright and dark fringes are parallel. Now, what are the factors on which the fringe width is dependent on? Clearly, since beta is equal to d lambda by d, here term m is not coming in, right? M is the order of the fringe. So clearly beta is independent of m, the order of the fringe. Beta is independent of m and beta is dependent on d. Beta is dependent on d, lambda and small d. Capital D is the distance between screen and the slit. Small d is the separation between the slits S1 and S2. D is the separation between the slits S1, S2 and the screen. And lambda is the wavelength of the light used. So these are the factors that determine the fringe width beta. So I hope that this concept of Young's double slit experiment is clear for you. We tried to understand the path difference between the two rays coming from two sources. We derived mathematical expression for delta, which is xd by d. From that we can write the conditions for constructive interference and the destructive interference. And finally, we obtained the expression for the fringe width beta. And that is what we have done today. Thank you.